A bulletproof vest is a type of body armor that helps absorb the impact and reduce or stop the penetration to the torso of a projectile, such as a bullet or shrapnel. Properties needed for this include high tensile strength, high toughness, lightweight, and resistance towards heat and corrosion. A typical bulletproof vest is made up of advanced plastic polymers that is composed of many layers such as Kevlar, SpectraShield, Twaron, or Dyneema. A company named Nelvana has created a material called ABC Matrix that is sold at a cheaper price than Kevlar, with a toughness similar to that of Kevlar. 1 yard of Kevlar costs around $54.95. Kevlar does not have any environmental impact as long as it is disposed of properly. If not disposed of properly and left in the landfill to decompose, it will take multiple years to decompose. It is also available to the public, and there are numerous stores where you can buy it.
Major properties of candidate materials. One of the most famous candidate materials for bulletproof vests is Kevlar. Kevlar is a synthetic polymer. Its density is only 1.44 and its specific tensile strength is 8.15. Its specific yield is 898.5, which is about 8 times stronger than that of titanium. You can see that from figure 3.6 that Kevlar has a very high tensile strength as well as yield strength. However, Kevlar is not very good at dealing with strong acids and bases. When facing strong acids and bases, degradation occurs for Kevlar. You can see that from figure 2.1. Since Kevlar is a polymer, it doesn't have a definite melting temperature. However, Kevlar starts to decompose at 472 to 482 degrees C. Just like most of polymers, Kevlar is very sensitive to UV light, and the excess exposure to UV light leads to discolor or even the loss of certain mechanical properties for Kevlar.
The production of the Kevlar bulletproof vests is both complex and interesting. The Kevlar is synthesized through the condensation reaction of the two monomers paraphenylenediamine and terephthalate chloride, and has a byproduct of hydrochloric acid. This reaction can be seen above. The polymerization creates a liquid crystalline substance that can be mechanically drawn into fibers in the polymer chain direction. To do this, sulfuric acid is used to keep the polymer in solution. Then machines use a showerhead-like fixture, shown in figure 1, to draw the polymer solution into its mechanical fibers. These fibers then go through a spinneret in figure 2 and are wound onto many spools. Finally, the Kevlar fibers can be processed in 2 different ways, depending on the desired material properties. They can be woven to produce a light and flexible material that is commonly used in shoulder straps, pockets, and the outer casing of the vests, or the fibers can be aligned, then infused with resin to form rigid panels that are lightweight and up to 20 times the strength of steel. Both of these processes are present in the final bulletproof vest, shown in figure 4.
Microstructure and its property relationship. First, microstructure. The basic structure of Kevlar is that of a polymer. Kevlar material depicts a microstructure of crystalline sheets that are pleated together via van der Waals and hydrogen bonding. These sheets are aligned in an axial orientation, and the surface benzene rings show a coplanar rotation in most of this crystalline structure. How this relates to its properties. The crystalline structure promotes its high tensile strength and toughness. Kevlar is spun similar to silk, resulting in these planar sheets. These sheets allow the material to have its high tensile strength. Comparatively, Kevlar has almost 50 times tensile strength of nylon and is 5 times stronger than steel by weight. These are due to the fully extended organic fibers above. And then, as you can see in the picture below, you can see the axial-oriented different crystalline structures going from bundle to fiber to microfiber and on.
Environmental interactions. Because the Kevlar fibers in bulletproof vests are so tightly woven, and there is sometimes an infused resin to increase the strength. They're not very flexible and are prone to negative effects from certain environmental conditions. So if the vest is flexed in such a way, these polymers will stretch and the vest will wear out and fatigue much faster, and that will lessen the ultimate strength and utility of it. And then it will also cause it to not always be 100% protective. So the bullets will be stopped, but there will be noticeable damage to the vest. It's also important to keep them away from water because water acts as a somewhat lubricant, allowing the bullets to kind of slip past the fibers much easier. But Kevlar was chosen as a material because it doesn't wear as fast as other materials. So Xylon was a synthetic polymer that was used at one point but recalled because it wears a lot faster under the same environmental conditions. Also, once the vest gets worn out, it is no longer effective. It has to be disposed of correctly because Kevlar is 100% recyclable. The fibers can be restrung and used for other purposes.
Our research proposal aims to provide insight on how woven materials accomplish the tasks required by bulletproof vests. This line of research would lead towards understanding the requirements of woven materials, helping propose realistic alternatives that improve cost, efficiency, or product organicness or recyclability. The important abilities of a bulletproof vest are to disperse the kinetic energy from a high-speed projectile and prevent foreign material from entering the body. A simple test that could be performed using the university's resources would be a penetration test on materials such as UHM, WPE, Kevlar, and aramid. This test would help reinforce our understanding of how bullets interact with woven materials such as Kevlar, as well as how kinetic energy is dispersed throughout woven materials.